What if the biggest secret to our existence, the very spark of our sprawling universe, isn't hidden in some mind-blowing cosmic explosion, but in, well, nothing? What if the void, that immense emptiness we see between stars and galaxies, isn't actually empty at all? Picture a canvas that looks blank, but is secretly alive, shimmering with a hidden energy. Imagine a restless sea from which everything we know, everything we are, could have emerged. This isn't just some philosophical riddle. We're talking about a journey to the cutting edge of physics, to an idea that redefines nothing and could potentially explain everything. The quantum vacuum. Get ready to question what you think you know about reality. We've always been told that something can't come from nothing. But what if nothing is actually the most powerful something in the entire cosmos? What if that silent, dark expanse that seems like the ultimate emptiness is, in fact, a bubbling cauldron of potential, a cosmic womb giving birth to particles and maybe even whole universes? This is the world of the quantum vacuum, a place where the usual rules of physics get seriously weird, and where the origins of everything might just be hiding. For centuries, nothing was pretty straightforward. An absence, an empty box, a silent room, those vast, dark stretches between stars. That was true nothingness. Philosophers and scientists chewed over this idea of absolute emptiness. Aristotle talked about horror vacui, the idea that nature hates a vacuum, hinting that true nothingness might be resisted by the cosmos. Still, the image of a passive, featureless void stuck around. If you could somehow suck out all the matter, all the energy, all the radiation, you'd be left with, well, nothing. A perfect, sterile, and honestly, pretty boring emptiness. But then came the 20th century, and with it, a revolution that blew that classical picture to smithereens: quantum mechanics. And quantum mechanics brought a totally new mind-bending take on the vacuum. Suddenly, nothing wasn't looking so empty anymore. The quantum vacuum, as physicists started to figure it out, is a long way from being a peaceful void. Instead, it's the lowest possible energy state of a quantum field. Don't think of it as an empty stage. Think of it as a stage where the lights are dimmed so low you can quite see the actors, but they're constantly moving, interacting. A subtle energetic dance happening just beyond what we can normally perceive. This new nothing is a seething, dynamic arena. According to quantum field theory, this ground state is absolutely buzzing with activity. Fields, which are the fundamental building blocks of reality, are constantly and out of these fluctuations, pairs of virtual particles and their antimatter twins are always popping in and out of existence. They are a direct result of one of the most basic principles in quantum mechanics, the Heisenberg uncertainty principle. This principle, in one of its forms, says there is a fundamental limit to how precisely we can know certain pairs of a particle's properties at the same time, like its energy, and for how long it has that energy. For incredibly tiny fractions of a second, energy can be borrowed from the vacuum to create these particle-antiparticle pairs. They then usually annihilate each other, paying back the energy debt almost instantly. Their existence is incredibly brief, often shorter than Planck time, the smallest unit of time that even makes sense in physics, but their combined effects are very real and totally measurable. So, the vacuum, this supposed nothingness, is actually a bubbling brew of potential. It's a restless medium, a fundamental layer of reality that's anything but empty. The old classical idea of a calm void has been kicked to the curb, replaced by the much more exciting, much more powerful concept of the quantum vacuum. It is a realm of subtle energies and fleeting particles that holds the key not just to the nature of empty space, but maybe even to the origin of everything we see around us. This isn't just playing with words. It's a complete rethink of the very fabric of existence. To really get a handle on how the quantum vacuum could shape the universe, we need to explore its strange and fascinating properties. This isn't just wild speculation. These are features with effects we can actually observe. Things that confirm the vacuum is more than just a blank spot in our theories. Zero-point energy. The universe's baseline. One of the most mind-boggling predictions of quantum mechanics is that even at absolute zero, the coldest temperature possible, where all classical movement should stop, quantum systems still have a tiny, irreducible bit of energy. This is called zero-point energy. Think of it like the quiet hum of a giant engine that never really turns off. Every single point in space, according to quantum field theory, has this leftover energy. This means the vacuum itself has an inherent energy, a baseline thrumming that fills the entire cosmos. Picture a guitar string. Pluck it, and it vibrates at specific frequencies. It's harmonics. But even when it looks perfectly still, quantum mechanics tells us it has these tiny, imperceptible jiggles. It's zero-point motion. The quantum vacuum is like an infinite orchestra of these quantum fields, each with its own zero-point energy, all adding up to an overall energy density for empty space. And this energy isn't just some quirky theoretical idea. It has huge implications. Virtual particles, the fleeting actors of reality, as we mentioned. The quantum vacuum is like a stage for the constant coming and going of virtual particles. These are antiparticles in the same way as the electrons and protons that make up the atoms we know. They're temporary disturbances, little ripples in the quantum fields, that exist for such short times. Thanks to the Heisenberg uncertainty principle, that you indirectly see them as stable, long-lasting particles. They borrow energy from the vacuum to pop into existence as particle-antiparticle pairs, and then quickly destroy each other, returning the energy to the vacuum. You might be wondering, if they're so short-lived and we can't see them directly, how do we even know they're real? Well, it's all about their indirect effects. Like a gust of wind you can't see but know is there because the leaves are rustling. Virtual particles leave their fingerprints on the world we can observe. The Casimir effect. Tangible proof of nothing's power. One of the most convincing experimental proofs that the quantum vacuum and its energy fluctuations are real is the Casimir effect. Predicted by Dutch physicist Hendrik Casimir back in 1948, and later confirmed by experiment. This effect shows a physical force that comes purely from the quantum vacuum. Imagine two uncharged, perfectly reflective metal plates placed incredibly close together in a vacuum, just micrometers apart. Classically, you wouldn't expect any force between them. But the quantum vacuum is filled with virtual photons of all possible wavelengths. The tiny space between the plates restricts the wavelengths of virtual photons that can exist there. Only those that fit just right are allowed. Outside the plates, there's no such restriction. This means there are more virtual photons pushing on the outside surfaces of the plates than on their inner surface. The result, a tiny, but measurable, attractive force pulling the plates together. This force isn't due to gravity or electromagnetism in the classical sense. It's a direct result of the zero-point energy of the quantum vacuum. The plates are literally being pushed together by the pressure of virtual particles. This is solid, physical proof that the vacuum isn't empty and actually exerts real forces. The quantum vacuum and the structure of matter. Beyond the Casimir effect, the quantum vacuum's influence is woven into the very fabric of how fundamental particles behave. For example, the charge we measure for an electron isn't its bare charge. The bare electron is constantly surrounded by a cloud of virtual particle-antiparticle pairs that it polarizes. This cloud effectively shields the bare charge, so what we measure is an effective charge at a given distance. This phenomenon, called vacuum polarization, affects how charged particles interact and is a vital part of the super-precise calculations in quantum electrodynamics, one of the most accurately tested theories in all of science. The quantum vacuum also has a say in how particles get their mass. While the Higgs field is the main player in giving fundamental particles mass, the way particles interact with the quantum vacuum fluctuations can also add to their observed mass. It's a complex dance, but the main message is clear. The vacuum isn't just a passive background. It's an active player in shaping the properties of matter. The quantum froth, as it's sometimes called, is a realm where our everyday intuition just doesn't cut it. It's a place of built-in uncertainty, of energy popping out of nowhere for fleeting moments, of forces generated by the very absence of matter in the classical sense. Getting a grip on these properties is the first step to understanding how this seemingly ghostly concept could be the architect of something as vast and solid as our universe. The puzzles of the quantum vacuum don't just stop at the tiny world of virtual particles. They stretch out to the grandest cosmic scales, possibly holding the key to one of the biggest mysteries in modern cosmology. For a good chunk of the 20th century, cosmologists thought the universe's expansion, which kicked off with the Big Bang, was gradually slowing down. It made sense. All the matter in the universe should be gravitationally pulling on everything else. The big question was whether there was enough stuff to eventually stop the expansion and cause a big crunch, or if the universe would just expand forever, though slower and slower. Then, in 1998, two separate teams of astronomers studying distant type Ia supernova stumbled upon something that rocked the scientific world and won them the Nobel Prize. These supernovae are like standard candles. We know their real brightness, which lets astronomers measure their distances. By also analyzing their redshift, they could figure out how fast they were moving away. The data showed something incredible. The expansion of the universe wasn't slowing down. It was speeding up. Something was pushing the universe apart, overpowering gravity's pull on cosmic scales. This mysterious something got the name dark energy. Later observations, like studies of the cosmic microwave background, the Big Bang's afterglow, and how galaxies are spread out on a large scale, have all confirmed this accelerated expansion. Right now, estimates suggest dark energy makes up about 68 to 70% of all the energy and matter in the universe. Dark matter takes up another 25 to 27%, and the normal, visible matter, stars, planets, US, is just a tiny 5%. We're living in a universe mostly made of stuff we don't really understand. So, what is this puzzling dark energy? This is where the quantum vacuum makes its grand re-entry. One of the top candidates for dark energy is the energy of the vacuum itself. That zero-point energy we talked about. Quantum field theory predicts that empty space should have its own inherent energy density because of all those quantum field fluctuations. This vacuum energy, if it's real, would have a weird property: negative pressure. In Einstein's theory of general relativity, which describes gravity, this negative pressure would act like a repulsive gravitational force, making space itself expand faster and faster. This idea actually links back to something Albert Einstein himself came up with in though for a totally different reason. When Einstein first wrote down his equations for general relativity, they predicted a dynamic universe, either expanding or contracting. But back then, everyone thought the universe was static. So, to make his equations fit a static universe, Einstein reluctantly added a cosmological constant. This term stood for a constant energy density inherent in space, which could balance out gravity and keep the universe stable. When Edwin Hubble discovered in 1929 that the universe was expanding, Einstein famously called the cosmological constant his biggest blunder. Well, science has a funny way of coming full circle. With the discovery of accelerated expansion, the cosmological constant, or something very much like it, has made a dramatic comeback. Now, it's seen as a measure of the vacuum energy density of the universe, providing that repulsive force driving cosmic acceleration. The quantum vacuum, far from being just some abstract theory, could be the very engine powering the universe's runaway expansion. However, this neat marriage of quantum theory and cosmology comes with a massive headache, often called the cosmological constant problem, or sometimes the vacuum catastrophe. When physicists try to calculate the expected energy density of the quantum vacuum based on quantum field theory, by adding up the zero-point energies of all known quantum fields up to a certain energy limit, the number they get is mind-bogglingly huge. The predicted value is about 120 orders of magnitude. That's a 1 followed by 120 zeros, larger than the value of dark energy density we actually observe from astronomy. This difference has been called the worst theoretical prediction in the history of physics. Why is there such an enormous gap? If the vacuum energy were really that immense, the universe should have ripped itself apart moments after the Big Bang, or collapsed into a singularity. The gentle acceleration we see means the actual vacuum energy density is incredibly tiny. Almost zero, but not quite. This cosmological constant problem is one of the deepest and most stubborn mysteries in fundamental physics. It hints that there's something major we're missing in our theories of gravity, quantum fields, or maybe both. Perhaps some unknown physical principle cancels out most of the vacuum energy, leaving just a tiny bit behind. There are plenty of theories floating around. Supersymmetry. This theory suggests a symmetry between fundamental particles called bosons and fermions. In a perfectly supersymmetric world, the contributions to vacuum energy from bosons and fermions would cancel each other out perfectly. The catch is, we haven't seen any supersymmetric partner particles, which means if SUSY exists, it must be a broken symmetry at the energies we can currently explore, and that complicates the cancellation. Anthropic principle. This idea suggests that we see a small cosmological constant because, in a huge multiverse with many universes, each having different physical constants, life could only pop up in universes where the vacuum energy is small enough for galaxies and stars to form. While some find this intriguing, others think it's an unsatisfying explanation, because it doesn't offer a basic physical reason. Modified gravity, asterisk, maybe Einstein's theory of general relativity needs tweaking on cosmic scales, or perhaps vacuum energy doesn't gravitate the way we assume it does. Dynamical dark energy, asterisk. What if dark energy is in a constant vacuum energy, but some dynamic field that changes over cosmic time? Recent observations from projects like the Dark Energy Spectroscopic Instrument have given some tantalizing hints, though nothing conclusive yet, that dark energy might indeed be evolving, possibly weakening over the last few billion years. If this is confirmed, it would rule out a simple cosmological constant and point towards new physics. This evolving dark energy could also potentially ease some of the tension with theoretical predictions of vacuum energy. Despite the cosmological constant problem, the link between the quantum vacuum and dark energy is still a very compelling area of research. The fact that empty space should have energy according to our best quantum theory, and that the universe is behaving as if it's filled with a diffuse, repulsive energy, is just too suggestive to ignore. Solving this puzzle probably holds the key to a deeper understanding of the fundamental nature of reality, bridging the gap between the quantum world and the cosmos as a whole. The quantum vacuum, it seems, isn't just a frothy sea of virtual particles, but a major player in the ultimate fate and evolution of our universe. We've looked at how energetic the quantum vacuum is and its potential role in making the universe expand faster. But could this buzzing nothingness do something even more amazing? Could it be the very source of the universe itself? This is the bold idea of quantum genesis, the universe being born from a hiccup in the quantum vacuum. The Big Bang model describes the universe evolving from an incredibly hot, dense state, but it doesn't really explain what banged, or what was around before the Big Bang, or even how that initial state came to be. This is where the quantum vacuum offers a tantalizing, though still speculative, possibility. A universe from a quantum fluctuation. Tryon's idea back in 1973. A physicist named Edward Tryon published a short but game-changing paper in the journal Nature. Its title is The Universe of Vacuum Fluctuation. Tryon suggested that our entire universe might just be a spontaneous quantum fluctuation in a pre-existing quantum vacuum. Basically, something that just happens from time to time. His thinking was partly based on a curious observation. The total energy of the universe seems to be astonishingly close to zero. Matter and radiation have positive energy. Gravity, on the other hand, can be thought of as having negative energy. Tryon proposed that the positive energy tied up in all the matter and radiation in the universe could be perfectly balanced by the negative gravitational potential energy. If the total energy is zero, then creating a universe from nothing doesn't actually violate the conservation of energy, as long as it happens as a quantum fluctuation. A temporary borrowing of energy is okay under quantum rules, much like those virtual particles briefly popping into existence, as long as the overall balance sheet stays at zero. At the time, Tryon's idea was met with a fair bit of skepticism, even some chuckles. But as our understanding of quantum field theory and early universe cosmology got better, especially with the development of inflationary theory, the notion of a universe popping out of a quantum event started to gain more ground. Inflation and the seeding of structure, the theory of cosmic inflation, put forward in the early 1980s by physicists like Alan Guth and Andre Linde, suggests that the very early universe went through a period of incredibly rapid, exponential expansion. This inflationary period, happening just tiny fractions of a second after the Big Bang, would have stretched the universe enormously. This stretching would have smoothed out any initial bumps, and explained several puzzling things about our cosmos, like why it's so remarkably flat and uniform on large scales. Inflationary cosmology gives us a powerful way to understand how quantum fluctuations in the super-early universe could have been stretched to astronomical sizes, becoming the seeds for all the structures we see today. Galaxies, clusters of galaxies, and that vast cosmic web. Even before inflation, this primordial state would have been full of quantum jitters. These tiny quantum fluctuations in density and energy, normally stuck at microscopic scales, would have been blown up by inflation to macroscopic, even cosmic, sizes. Regions that were a tiny bit denser would, after inflation, act as gravitational seeds, pulling in more matter and eventually collapsing to form the galaxies and galaxy clusters we see. Those tiny temperature variations across the sky seen in the cosmic microwave background radiation are believed to be the imprints of these primordial quantum fluctuations. A snapshot of the universe when it was just 380,000 years old. This gives strong observational backing to the whole picture. Researchers are even using quantum computers now to simulate how quantum fluctuations in an expanding space-time can lead to particle creation, giving us new tools to study these very early universe processes. So, if inflation blew up quantum fluctuations, Could a quantum fluctuation have actually kicked off inflation and the Big Bang itself? This is where models of quantum creation enter the scene. Alexander Vilenkin, for example, proposed that the universe could have tunneled into existence from a state of nothing, where nothing means no classical space-time, matter, or energy, but perhaps still subject to the laws of quantum mechanics. Quantum tunneling is a real thing where a particle can pass through an energy barrier it classically shouldn't be able to. Vilenkin suggested the universe itself could have popped up through a similar quantum process, spontaneously appearing from a state of non-being without needing a pre-existing vacuum in the usual sense. The quantum vacuum as the ultimate precursor. In these quantum genesis scenarios, the quantum vacuum plays a starring role. It's not just the empty space within our universe, but potentially the fundamental fabric from which space-time itself emerged. Some theories even suggest that space and time aren't fundamental at all, but are emergent properties arising from more basic quantum bits and pieces. The quantum vacuum, in this view, isn't just in space. It is the potential from which space crystallizes. The idea that the universe, with all its incredible vastness and complexity, could have sprung from a quantum hiccup in a pre-existing state of nothingness is perhaps the most profound takeaway from quantum physics. It messes with our deepest intuitions about cause and effect and what it means to exist. While these theories are at the very edge of theoretical physics, and do you want to have direct experimental proof yet, they offer a scientifically grounded way to tackle the ultimate question of where everything came from. They suggest that the nothing of the quantum vacuum isn't an end, but a beginning, a restless, energetic void pregnant with the possibility of creating everything. If our universe really could spring forth from a quantum fluctuation in the vacuum, the consequences aren't just profound, they're potentially The idea of quantum genesis doesn't just give us an origin story for our cosmos, it throws open the door to the mind-boggling possibility of a multiverse. The landscape of string theory and eternal inflation, modern cosmological theories, especially those that bring in string theory, suggest that the quantum vacuum might be way more complex than just a single, unique state. String theory, which says fundamental particles are tiny vibrating strings, predicts a huge landscape of possible vacuum states. Maybe 10,500 or even more. Each of these different vacuums could correspond to a different set of physical laws, different fundamental constants, and even a different number of spatial dimensions. Our universe, with its specific laws and constants, would then just be one realized state among an unbelievably vast array of possibilities. Combine this with the idea of eternal inflation, and you get a picture of a kind of cosmic fractal. Eternal inflation suggests that while inflation ended in our observable patch of the universe, allowing it to cool down and form stars and galaxies, it might be continuing indefinitely in other regions, far beyond our cosmic horizon. As these regions inflate, they could decay into different vacuum states from that landscape, spawning new bubble universes, each with potentially different physical properties. Our universe would then be just one bubble in an immense, ever-expanding cosmic foam, a multiverse of disconnected or perhaps subtly interacting realms. If a quantum fluctuation can create one universe, why not tons of them? The quantum vacuum, in this picture, acts like a fertile breeding ground, constantly giving birth to new universes. Each Big Bang might just be one event in an ongoing, eternal process of cosmic creation, all driven by the underlying physics of the vacuum and inflation. Asterisk, twin universes and CPT symmetry, a mirrored creation. Asterisk, a really fascinating and more recent idea in quantum genesis models involves something called CPT symmetry and the birth of twin universes. CPT symmetry is a fundamental symmetry of physical laws when you combine three operations: charge conjugation, parity inversion, and time reversal. It's thought to be an exact symmetry of nature. Some cosmological models propose that our universe might not have been born alone, but as one half of a universe, anti-universe pair, both popping out simultaneously from the quantum vacuum. In such a scenario, this anti-universe would essentially be the CPT image of our own. It might be dominated by antimatter and, most strikingly, could be evolving backward in time relative to us. This idea, explored in models sometimes called quantum genesis cosmology, suggests a perfectly symmetric creation from nothing, where the total conserved quantities of the pair remain zero, totally consistent with an origin from the vacuum. These models offer some pretty neat solutions to cosmological puzzles. For instance, that observed asymmetry between matter and antimatter in our universe could be explained if the missing antimatter is just chilling in this CPT. What's more, such models can replace the problematic initial singularity of the Big Bang, that point of infinite density and temperature where physics just breaks down, with a smooth, finite quantum process, maybe a bounce or a transition from a timeless Euclidean state. The entanglement between our universe and its mirror twin could also have effects we could observe, potentially influencing things like dark matter or dark energy. Some researchers are even looking into whether subtle imprints of such a twin universe might be detectable in the cosmic microwave background or the large-scale structure of galaxies. While this is definitely out there, these theories are mathematically solid and really push the boundaries of how we think about cosmic origins, grounding them in fundamental symmetries and quantum principles. Philosophical and existential reflections, the idea that our universe, and maybe countless others, came from the nothingness of the quantum vacuum carries some serious philosophical weight. It totally if universes are just a natural consequence of the laws of physics acting on the vacuum state, then our existence, while incredibly precious, might not be some singular, miraculous event, but part of a much grander, ongoing cosmic show. It also blurs the line between nothing and something. If the vacuum is the source of all existence, then nothing is the ultimate something, the foundational reality. This perspective challenges traditional creation stories and forces us to consider that the universe might not need an external creator in the classical sense, but can arise from the inherent properties of physical law itself. Of course, it's worth remembering that quantum nothingness isn't absolute nothingness. It's a state governed by quantum laws, a physical vacuum. The question of why those laws exist, or why there's a quantum vacuum with these properties in the first place, just pushes us to even deeper levels of head-scratching. The implications are pretty wild. A multiverse of worlds, twin realities, a cosmos born from the subtle hum of quantum fields. The quantum vacuum, once thought of as the ultimate emptiness, now looks like a boundless wellspring of creation. It's a testament to the universe's capacity for self-generation, constantly hinting at secrets still waiting to be discovered. These ideas, while on the cutting edge of scientific speculation, highlight the power of human curiosity to probe the deepest mysteries of existence. Armed with math, observation, and an unstoppable desire to understand where we came from and what the universe truly is. From what we thought was an empty void to a seething ocean of virtual particles and zero-point energy, the quantum vacuum has completely flipped our understanding of nothing. We've journeyed through its bizarre properties, like the Casimir effect, which gives us real proof of its energetic nature. We've seen how this vacuum energy is the top suspect for the mysterious dark energy that's making our universe expand faster and faster, even if it comes with that tricky cosmological constant problem. Most incredibly, we've explored the game-changing idea that the quantum vacuum could be the actual parent of our universe, a quantum fluctuation that sparked the Big Bang and gave rise to everything we see. And this creation story might not be a one-off event, potentially leading to a vast multiverse, or even a CPT-symmetric twin universe, forever linked to our own. What started as a mission to understand emptiness has led us to the very foundation of reality. It suggests that nothing is, in fact, the secret to everything. The quantum vacuum isn't just some passive stage. It's an active, dynamic entity, the ultimate source from which physical laws and the very fabric of space-time might emerge. Our journey into the quantum vacuum is far from finished. So many questions are still hanging in the air. What's the real solution to the cosmological constant problem? Can we find direct evidence for quantum genesis or the existence of other universes? Will new breakthroughs in quantum gravity finally unite the tiny world of quantum mechanics with the giant realm of Einstein's relativity, giving us a complete picture of creation? The secrets of the universe are slowly giving way to our relentless curiosity, and the quantum vacuum stands as a powerful reminder of how profound and often counterintuitive reality can be. It shows us that even in what seems like the most desolate emptiness, there lies an unimaginable potential, a fundamental restlessness that could be the source of all wonder. If this dive into the quantum vacuum has expanded your mind, be sure to like this video, subscribe for more journeys into the secrets of the universe, and share your thoughts in the comments below. What part of the quantum vacuum blows your mind the most? Do you think our universe is just one of many out there? Let's keep the conversation going. The enduring mystery of creation keeps calling to us, and the quantum vacuum, once the symbol of nothingness, now shines as perhaps the most fertile ground for discovery. The universe isn't obliged to make sense to us. But with every new insight, we get a tiny bit closer to understanding its deepest truths, hidden in plain sight, in the very fabric of the void.